In section 2.3, we're really taking a look at mathematical arguments, well, and arguments in general, but towards the goal of understanding precise mathematical arguments. So we're going to have, we're going to take a look at argument structure, the premises, the conclusions, and we're going to introduce some precise terminology that helps us describe whether the argument is good or not. So validity versus soundness is going to be a couple of really important ideas. Rules of inference are sort of the like engines of the argument, and then we'll talk about some errors that can occur in arguments. So here's an argument, and let's look at the structure of the argument carefully. So the first premise that we're writing down here, sort of assumption or hypothesis, is that if the discriminant of this quadratic equation is non-negative, by non-negative I mean just not a negative number, so either 0 or positive is what non-negative means. So if the discriminant of this quadratic equation is non-negative, then the equation has a real root. So you may remember from algebra class that this is like a true statement, that anytime you have a non-negative discriminant, you will have an equation, a root to the equation. And then the second premise that I'm writing down here is that indeed this quadratic equation does have a non-negative discriminant. So these two statements put together form the premises of the argument, and from them I'm concluding that this quadratic equation has a real root. So a very simple sequence of sentences, they together form what's called an argument. The two starting sentences are called the premises. Those are the things that I am assuming, and then from those two premises I draw the conclusion that the equation has a real root. So let's put some symbols to this just to see what form it takes. The first premise is an if-then statement, where the P part is that the discriminant of the equation is non-negative, and the Q part is that the equation has a real root. The second premise then is just the P statement, and the conclusion here is the Q statement. So the overall form of the argument is first premise, P implies Q, second premise, P, therefore conclusion Q. This argument feels like it's good, I guess. I believe that it's sort of logically valid as I read through it. Indeed, it is a valid argument. We'll talk more about validity later, but this form, P implies Q, P, therefore Q, is called modus ponens. And all of the valid argument forms are listed on page 61, so make sure you know them all. All right, let me sort of write out another modus ponens argument, but something is going to be a little bit strange about this one. So first premise is that if the number 7 is prime, then the number 6 is prime. The second premise is that the number 7 is prime, and from this I'm concluding the conclusion the number 6 is prime. Now let me look at the pieces here. The first premise is an if-then statement with P representing 7's prime, Q representing 6's prime, and the second premise being P, conclusion Q. So it has exactly the same form as the previous argument. It's modus ponens, P implies Q, P, therefore Q. But something's weird about this argument because it seems to be bad in some sense. It's still a valid argument, and that's the weird thing. You gotta distinguish validity with soundness. I'll explain that in a second. But the problem is that the first premise is a false statement, and that sort of makes the whole argument break down, right? So take a look at the first premise. If the number 7 is prime, then 6 is prime. It's a conditional statement. The P part of it's true, and the Q part of it is false. When a conditional has those two truth values in the P and Q, we know it registers as false. So we start with a false premise, and then we add on to it another true premise, and from those two premises we conclude, using modus ponens, a false conclusion. So the fact that we have that false premise in there prevents the argument from being what's called sound or good, even though it has a good valid argument form. So the argument form is perfectly good, it's just that one of our premises is false. Okay, so the point that I'm obviously trying to drive home here is that just because an argument is valid doesn't mean that it's sound. So a valid argument could very well be unsound. You got to take a look at the truth values of the premises. And in mathematics, we're interested in making sound arguments, so those that are valid and have true premises. Right here we have a sound argument. I've just changed the quadratic argument slightly to make sure that I know that the premises are both true. So I'm looking at a specific quadratic here. It has a non-negative discriminant, and it is true that if a discriminant of a quadratic is non-negative, it has a real root. So both of my premises are true, and it's in the form of modus ponens. So this is a valid argument. These are exactly the types of arguments I want to be making in mathematics. So again, what I mean by sound argument is that I have true premises and valid argument forms. Let's take a look now at the kind of arguments we don't want to be making in mathematics, that is unsound arguments. So here, positive, it means not negative and not zero. So it is true that if a quadratic equation has a positive discriminant, it definitely has a real root. And it is true that that equation, x squared minus 2x plus 1, has a real root. So I've got two true premises, but the conclusion that x squared minus 2x plus 1 has a positive discriminant is not true. Actually, it has a zero discriminant. So the problem with this argument is that the argument form is actually not valid. So we'll see this in a truth table a little bit later, but you can't have an invalid argument form together with true premises and expect to be making a good argument. So that argument's unsound for that reason. Moving on to the last one, I have another unsound argument which really sneaks up on us. I've got true premises and a true conclusion, but again, I have this invalid argument form making the entire argument just bad, right? We call it unsound for that reason. So true premises, a true conclusion, because in that quadratic I do have a positive discriminant, but it's still of this invalid argument form. So let me write out this invalid form so you can see what's going on here. My first premise is of the form P implies Q, but the second premise is Q. And from this, I cannot draw the conclusion P. This is an argument error called a converse error. And again, I'll specify more precisely what I mean by invalid argument by using a truth table in a second, but this P implies Q, Q, therefore P is simply not good logic. It is not a valid argument form. There's another error to look out for. It's called an inverse error. So if you have a premise P implies Q and you have a premise not P, you cannot conclude not Q from it. Let's start talking about what it means to be a valid argument now. So a valid argument is going to mean that when you put together true premises, you're guaranteed to get a true conclusion. So if I construct a truth table and just inspect the truth values of the premises and the conclusion, I can inspect whether an argument form is valid or not. So when I construct the truth table, I'm going to look at the columns associated with the premises and just check to see, is it the case that when the premises are all true, is it the case that the conclusion is also true? So anytime that you have an argument form that satisfies that, we're going to call it valid. And if it's the case that the premises of an argument form could be true while the conclusion could be false, then we'll call it invalid. All right, let's take a look at using a truth table to verify that the valid argument form of modus tollens is valid. So I'm going to need two predicates P and Q, so I'm just going to set up a truth table for that. And the modus tollens argument takes an implication P implies Q and another premise not Q and deduces from that not P. So I'm putting all of these things into my truth table, not Q, not P, P implies Q. And again, after I get the truth table filled out, what I'm going to do is identify those rows of the truth table in which both premises of modus tollens are true, and just check the conclusion, which will be not P in this case, is also true in those rows. So here's what modus tollens is. P implies Q, not Q, therefore not P. So these are the two premises. Let me identify them in the truth table. I've got P implies Q and there's not Q. And those are simultaneously true just in one row, in the very last row. Is it the case that the conclusion is also true in that row? Yes. Not P, the conclusion, happens to be true when both of those premises are true. So that's what I'm looking for. I have got here a valid argument form because the conclusion is true whenever both premises are true. So I would say that the argument form of modus tollens is valid because of this verification. You can do the same thing with modus ponens or any of the valid forms on 61, and I do recommend that you go through as many of those exercises as possible to see that this is a very precise term here, what validity actually means. Let's go ahead and see how we can use a truth table to see when an argument form is invalid. So I'll go ahead and choose one of my common errors and fill out a chart to verify that. So again, I'm going to set up a chart with two predicates P and Q and write out both the premises and conclusion of an argument form, and I'm looking for rows that coincide with both premises being true and taking a look at the conclusion and seeing if it's true or false. So let's inspect inverse error. Inverse error has premises P implies Q, not P, and the conclusion not Q. So I identify the two premises in the chart, so that's the third and fifth column, and I find where both of those premises are true. So there are two rows that have both premises being true, the second to last and the last. And unfortunately, the conclusion not Q is false in one of those situations. So I just need to find one instance of the premises being true while the conclusion is false to demonstrate that this argument form is invalid. So I draw this conclusion now that the inverse error argument is invalid, because if you look at the situation where P is a false predicate and Q is true, then both of the premises end up being true. P implies Q and not P are both true, but the conclusion is false. So this is how you use a truth table, an example from a truth table, to show that an argument form is. So finally, I want to go through an exercise to help us become fluent with building arguments. So what I have here is an exercise from section 2.3. I've got a bunch of premises listed here and a conclusion I'm supposed to draw from those premises. So I want to go through very carefully making a sequence of valid arguments, citing each of those arguments as I apply them. So I'm going to observe that one of the premises is R or S, that's premise B, and that taken together with the premise not S, which is E, I can join those two together using elimination and conclude R. So I right now have a new sort of premise that I can use that was concluded from two others, that is R. Not Q or S is also a given premise, that's D, and when I pair that together with not S, again, I can use elimination to conclude not Q. And look, I'm justifying precisely how I concluded not Q. It was from line 2 and 4 and the valid argument form of elimination. So continuing on, I'm just scanning my premises for something that I can use. I've got the premise P implies Q, that's A, and when I put that together with one that I've just concluded, not Q, I can use modus tollens to conclude not P. So now we'll put together two pieces that we've deduced here. We've got not P from line 7, and then we also have R from line 3. So citing 3 and 7 in conjunction, I come with the conclusion not P and R. Now let's scan our premises to see what else we have. We do have that not P and R implies U. That's premise F. I can therefore apply modus ponens together with 8 and 9 to conclude U. Okay, back to the premises to see what I have. I have not S implies not T. That's premise C. And I already have not S, so I can conclude from that, again with modus ponens, not T. So citing lines 2 and 11 and modus ponens, I conclude not T. Finally, W or T is a premise, it's premise G, and since I have not T, elimination will allow me to conclude W, so that's 12 and 13 in elimination together. And then with conjunction, I can put together lines 10 and 14 to get the conclusion that I was after, W and U. Okay, use this model when you're doing the homework problem that is like this. And in particular, make sure your justification column is very clear.